Hi, this is the last model of the spatial continuity analysis. In last lecture, you have seen how to estimate variograms based on a limited set of samples, what we call experimental variograms. Now, in this lecture, we are going to see how to fit a model to the experimental variogram values. Now here comes the question, why do we need a model of the variogram? And the answer is simple and straightforward. Just because experimental variograms are estimators of the spatial continuity pattern of the samples. It means that it represents the spatial pattern continuity at sample location. Now, for the spatial interpolation or spatial inference, what we call kriging, that we are going to see in the next part of this course, we'll need to know the variogram values for a pair of points at any spatial location of the study area. Hence, we need a model of the variogram which is valid for the entire region of study. Not only valid for the sample data location. In short, we are going to see the most common models to fit individual variograms, the models to fit the anisotropic patterns, models of anisotropy, and also we'll see some practical issues that we need to observe in this practice that someone called the art of infer variogram, because in fact this is not only a mathematical exercise that you are going to see. This is the last model of spatial continuity analysis, the variogram models. As you have already seen, with spatial continuity analysis, one intends to reach two main objectives. The first one here, we call it structural analysis, which goal is to understand and quantify the main patterns of the spatial phenomena, main direction of continuity, anisotropic behavioral internal properties, etc. That's what we have seen in the last lectures. The second objective consists on capitalizing the spatial pattern knowledge of the previous step and summarizing it in a spatial correlation model representative of the entire area, which is the basis of the geostatistical estimation and simulation models that we'll see later on. Now, how to get a model from the experimental variograms? The objective is to infer the real unknown variogram based on the values of the experimental variogram. Suppose we know the reality, this one, represented here by this image. We have some samples from the reality, for example, these ones. And we build experimental variograms, just one direction, for example, this one. But if we knew the reality, we could get the real variogram of the same direction. This one, here. This is the real variogram. Hence, the objective of this step is to know how to infer the real variogram, this one, based just on the only knowledge we have, which is the experimental variogram. Of course, this is a regression exercise, but it is important to note that this is much more than a simple regression exercise. The parameters of the variogram model must be related with physical phenomena and must be considered representative of the entire area, the unsampled locations. So we wish to interpolate the experimental points by a smooth curve, the variogram model, gamma of h. But this model must somehow be related with physical phenomena. Now, here they are some boundaries in this regression exercise. practical rules of thumb. The first one is the variogram model must be a function of small number of parameters. The law of parsimony, also known by Occam's razor, is a principle that states that in a problem, choose the solution. You should choose the solution with the fewest assumptions and parameters, because it's more easy to understand and tends to be the correct one. And these parameters here must be preferentially linked to the physical phenomena. Second rule, the variogram model must be representative of the spatial pattern of the unknown reality. It means that there must be a good estimator of the real variogram, not only a good interpolator of the variogram values. This means that we must add the experimental, the expert knowledge of the physical phenomena to this experimental, to this interpolation exercise. This is an important and crucial step of a geostatistical study. As the reality is unknown, normally a multidisciplinary team of experts, those ones, in the field of work is involved in order to squeeze all the knowledge about the phenomena into the variogram model. After this point, all steps of any geostatistical study use no more the experimental variogram values, but the spatial representative model of the entire study area. Now, to perform this fitting, any reliable geostatistical software can be used. But important is to put in mind that we are choosing a function, the variogram model, which parameters are somehow related with the main features of the phenomena you are analyzing. Another important point is to emphasize is that we wish to build a spatial correlation model representative of the entire area, which is the basis of geostatistical estimation and simulation models that you will see in the next parts of this course. As you are going to see, only some functions are permissible for that job. They must be positive, definite variogram models. Of course, you can take your time to create other possible and permissible functions to interpolate your experimental variograms. But it is better to invest your time trying to choose among the known models the most appropriate to your case study. We are going to see some more used models which cover the most of situations of natural physical phenomena. The spherical model, exponential model, Gaussian model. Of course, you can take your time to create other possible and permissible functions to interpolate your experimental variograms. But it is better to invest your time trying to choose among the known models the most appropriated to your case studies. Now you are going to see some more used models which cover the most situations of natural physical phenomena. Spherical model, exponential model, Gaussian model. Now let us start by the spherical model, maybe the most common model used in geostatistics. This image here represents the reality, an image of the spatial dispersion of a given property we are studying. This is a typical phenomena characterized by a fast transition from the high values to the low values. And this is here, the variogram in blue line, the corresponding variogram, the green here, the experimental variogram of all image, and the blue, the model. This is an omnidirectional variogram. This is a function of two parameters, the range A and seal C. We can consider the range as the lag distance. After that, we can consider that there's no correlation between samples separated by those distances above A. The value of the variogram model stays in a seal C after the range A, that it means here. The seal is the measure of the seal C is the measure of maximum variability, usually corresponds to the a priori variance. Note that after the behavior of the variogram, those fluctuations here are usually meaningless. They are statistically less consistent, less points, as you have seen in previous lectures, and also they belong to the part of the variogram with very low influence in posterior steps of estimation and simulation that you are going to see afterwards. This is the reason why they are modeled by a plateau. Yeah, this one. Here you can compare two images with the same spatial patterns but different dimensions. One with smaller bodies here of high and low values than this one. Both are modeled by the spherical models, but with the same seal, see? Okay, but with different ranges, 1,000 meters, 2,000 meters, which means that the lower, the bottom image has larger bodies of high and low values than the upper image here. This is the second model, the exponential model, which fits this kind of patterns here. A typical phenomena characterized by by a transition which is even more abrupt than the previous one at the beginning, very fast at the beginning, and after it flattens out more gradually, as you can see. And this is the model with a kind of inflection point. This is the variogram corresponding to that image. This is the model with this kind of inflection point here, the very fast transition, a very fast drop of correlation, and after a very slow transition to the seal. Which means the seal C is reached asymptotically. The practical range A is defined as the distance to which the model reaches 95% of the seal. Similar to the previous case, here we compare two images with different spatial patterns. Larger patterns here in bottom picture. Both are modeled by exponential model with the same seal, okay, but with different ranges. The bottom pictures with larger features have a range value twice the value of one of the upper image here. Here we compare the image fitted by spherical, and this one in the first column, and exponential models with the same ranges here, where we can notice the more fast transition at small scale and the slow transition from the high values to the low values. So when an inflection in the behavior of the experimental variogram is detected, one can get a better fit with the exponential variogram. Now, this is the third model, and this is a totally different phenomenon, characterized by very high spatial homogeneity. This is not very common phenomenon in earth sciences, but it's typical of, for example, the spatial dispersion of temperatures, precipitation of a given region. In earth science, you can find these kind of situations, these kind of patterns in sedimentary environments, like, for example, top and bottom and thickness of sedimentary layers. And these are fitted by what we call the Gaussian model, this one here, with this kind of parabolic near the origin characteristic. This is characteristic of very high spatial continuity. You can compare two different situations as we did in the last examples, with low low range of 1000 meters and high range of 2000 meters. Sometimes when we notice an inflection of the experimental variogram behavior like this one, this can also be modeled by a sum of structure called nested structure here. Look at this example. For example, the sum of the spherical model, this one here, with a range of 500 meters, if you do the averaging of those two, well, with this model of 2000 meters, we can get this one here, which is where we can notice the small bodies produced by the range of 500 meters, and also the clusters of those bodies compose large structures of 2000 meters. But the nested structures can result from weighted averages of the single structures. See the comparison, for example, of one arithmetic average with equal weights of both structures, with this one with the more weight, 70% of the large structures of 2000 meters range. Here we notice a much better definition of those clusters, of large clusters. In short, when you notice one or more inflection points in the experimental variograms behavior, we can try the fitting of the nested structure. Now, this represents those situations of very high variability at very short distances. In other words, the transition at small scale produces a jump, this jump here, of the variogram at the origin. This is called nugget effect. Nugget effect is a constant, here, this one, C0, that has to be added to other structures, event or structures. Nugget effect is what we call part of the total variability that usually we are not able to capture with our sample data. See this extreme example where the nugget effect is equal to the CIL, this one here. It represents a totally random spatial phenomena. Not that this is very hard to be observed in natural phenomena, unless the man have put their hands on it. But this represents a situation where the nugget effect represents after this one here, of the total variability. This is extremely important. This is extremely important to model appropriately this parameter, the nugget effect, because it represents a lack of our knowledge about the phenomena. And it has a very high impact of the posterior steps of a geostatistical study, like the spatial estimation. Now let us see the anisotropic patterns, when the spatial variability is not the same in all directions. It means that we are not in presence of isotropic phenomena. Now, how to create a model of this? So let's put the laser of these anisotropy patterns. Anisotropy model consists on calculating one single variogram model valid for all directions. After identifying the directions of the anisotropy, the next step consists on combining the various directional models into one single model consistent in all directions. Let's see, in this case here, we have, for example, the main axis of anisotropy, this north-south, the highest homogeneity, with this variogram here, with the highest range of 1000 meters. And the minor x, this one, the orthogonal one, east-west, with the same model, a spherical model here, but with just a 500 meters range. As the model are the same but with just different ranges, the variogram values are equal but in both models if the distance h are multiplied in this case by the ratio of anisotropy. In this case we are in presence of what we call geometric anisotropy model, which consists just on a simple transformation of coordinates, as you are going to see. Now, if we stretch the domain until it reaches the double of the dimension in east-west direction, for example, this one, equivalent to the ratio A1 over A2, we'll get one isotropic structure, one single variogram model, valid for all directions. That is the purpose of the anisotropy model. In short, when we have the same model but different ranges in orthogonal directions, the anisotropy model consists just one single geometric transformation. Now we're going to see another different type of anisotropy structure, the zonal anisotropy. Some sedimentary structures present high spatial horizontal continuity. This one in this picture here, 3D picture. High spatial continuity inside each layer and high heterogeneity between layers. In this case, the horizontal variogram are calculated basically inside each layer. They do not cross heterogeneous values between layers. As a consequence, the horizontal variograms are calculated inside each layer. They do not reach the seal value. The vertical variogram, as it crosses all the layers, this one here, it reaches the seal value here, equivalent to the maximum variability, the variance. This is what we call zonal anisotropy, very high homogeneity inside zones or layers in this case, and high heterogeneity between the layers. This zonal anisotropy can be modeled, for example, by a sum of two structures. One of them, extremely homogeneous, is responsible for the gap, this gap here. For the gap between the global seal C and the lower seal of the homogeneous layer, C1. Note that this very high range here does not affect the model at the spatial scale of the study area. And here we have the two structures at vertical direction. In short, a global variogram can be modeled by the sum of two geometric anisotropic structures here. Let us summarize the variogram model lecture. This is an exercise of fitting the most appropriate model among the known models to the experimental variograms. For example, linear behavior. Near the origin, we know that we are maybe in presence of a spherical or exponential model as the most appropriated one. Parabolic behavior near the origin, just this one here, just announces the Gaussian variogram, maybe the Gaussian variogram. Also, we look for the nugget effect and so on. But in any situation, no matter the feature we choose as an important one, it is always wise to look for a physical explanation. The feature may be spurious. In this inflection point here, in this case, a sum of structure can be adopted, or just an exponential model is sufficient. Normally, normally we start by the easiest model, which is assuming the variograms are the same behavior, have the same behavior in all directions. I mean, assuming they are isotropic. But in case variograms have different behaviors in different directions, anisotropy models must be fitted. But let us emphasize, the objective of this fitting exercise is to capture the main spatial patterns of the phenomena, not just to build a function that better fits the experimental points. A final note about these situations of what we call proportional effect, where locally we can observe high local means and variance. In the transition zones, these ones here, this pair of points can originate high spikes of variogram values for short distances. This can jeopardize the experimental variogram estimators. To mitigate those situations, you can find some equivalent tools that minimize those effects. The relative variogram, for a local relative variogram, this one here, and pairwise relative variogram, where the denominator here, this one, reduces the influence of very large values here. Just a final remark about the references. Of course, I recommend this book, the Introduction to Applied Geostatistics of Exacts and Srivastava. And for the readers in Portuguese, we can have this book, Geostatística para as Ciências da Terra e do Ambiente.